This is part 6 of the calculus section of our aero engineering course. We're going to use calculus to figure out how strong a rectangular cross section is. Instead of dividing this 2 inches by 2 inches above the centroid line into a bunch of 1/8 inch increments and estimating the strength of each one and adding them up, we're going to use calculus to integrate an infinite number of little slivers between the centroid and the top edge. Okay, so let's let dm equal our little incremental amount of bending moment attributable to this sliver that we've arbitrarily drawn there. We could draw it down here, we could draw it up there, it could be drawn anywhere between the centroid and the top of the board. Okay, dm is equal to the area of the sliver right there. Go ahead and darken it in a little. Okay, times the stress in the sliver, which is going to be somewhere between the stress at the centroid, which is 0, and the stress at the top edge, which is maximum. Okay, times the moment arm. Okay, dm equals area of the sliver times stress of the sliver times the distance between the sliver and the centroid, the moment arm, which is h in this case. So area is the width times the height of our sliver. Well, it's w wide, which is 2 inches. In this case, it's 2 before. You just say w times dh. That times that. That's the area of that little increment of sliver. The stress in our sliver is going to be the maximum stress multiplied by that distance divided by that distance. Because the stress here is 0, stress here is max. The stress between there and there depends on where it is. So the stress at the sliver is maximum stress times the distance there, which is h, divided by the distance there, which is 0.5 times capital H. Okay, now the moment arm, the distance between our sliver and our centroid, is just simply lowercase h. So we have dm, our little increment of bending moment, equals wdh times s max, maximum stress, stress at the top of the board, times, okay, we have a divided by 0.5, so we can multiply the top by 2 and multiply the bottom by 2. It won't change things. So we can say times 2h over 0.5 times 2, which is 1, so it just disappears. So we still have our capital H under there, times our little lowercase h. Okay, let's rearrange our formula so that all the things that are not functions of h are moved to the left. Okay, stress max, that's the stress at the top of the board. It's not a function of h. It's 4460 pounds per square inch, wasn't it, for this sugar pine? Okay, 2 is not a function of h. And w, the width across there, is not a function of h. So let's say dm equals 2 times maximum stress times w over h times h squared dh. Okay, these are all constants, so this is what we want to integrate, h squared over, or h squared times dh. So the integral of dm is m. M equals the integral of all that, which is just bring all this stuff straight down. 2 times maximum stress times w over capital H times the integral of h squared dh, which is h cubed over 3. Okay, and our limits of integration are from h equals 0 to h equals capital H over 2. So now we plug 0.5 times capital H into the little h spot here, because that's our upper limit of integration. And we see what we have, and then we subtract this equation with 0 put in the h cubed spot. So we have m equals 2 times maximum stress times W times 0.5 times capital H, all that in parentheses cubed, okay, over 3 times capital H minus this whole string of things with a 0 stuck in there, 2 times S max times W times 0 cubed over 3h. Well, obviously 0 cubed is 0, and multiply anything times 0 and you get 0, so this part of the equation just disappears because it's worthless. There's nothing to it. So what we have is this: 2 times maximum stress times W times 0.5 times capital H cubed over 3h. So when we multiply 0.5h times 0.5h times 0.5h, which is what 0.5h cubed is, we have 1/2 times 1/2 times 1/2, which is 1/8 h cubed. We just carry this same old stuff over, 2 times stress max times W over 3h. Okay, so if we have 2 times 1/8, that's 2/8, which is 1/4, and 1/4 divided by 3 is 1/12. So we have the same old stuff, W times S max times h cubed over 12h, and h cubed over h is h squared. So we have our bending moment is stress max times W times h squared over 12. But that's the bending moment just for half of a board. We have a bottom half of this board that's also contributing to the bending moment. If the top half's in tension, the bottom half's in compression. They're working together, so our total bending moment, let's just run out of room here, so we'll just let that M represent our total bending moment, which is just twice this. We just took this and multiplied it times 2. 2 times stress max times W times h squared over 12 is what we have here. And of course 2 over 12 is 1 over 6. So that's our formula for the bending moment of a rectangular cross section. And here's our old formula that we used earlier. Bending moment equals stress times Z, which is section modulus. Well, stress in this case is maximum stress. Okay, and Z is section modulus. So, as you can see, that stress max there is that, and that W times height squared over 6, that's what our section modulus is for a rectangular beam, as we use the same formula earlier. Z equals BH squared over 6. So I call it W this time. Width, base, doesn't really matter. That times that squared over 6 is your section modulus. Here's a chart that shows the section modulus of various cross sections. As we figured out a while ago, this rectangular cross section, the section modulus is that times that squared over 6. Here they call it base times depth squared. We called it height a while ago. It doesn't matter what you call it. That times that divided by 6 gives you your section modulus for a rectangular cross section. Here's a rectangular cross section that's hollow. That's what you'd have when you have a hollow tube, square tube. As you can see, this part of, here's what the section modulus is. This part of the equation is the same as this. That's base times depth squared over 6. Well, this is base times depth cubed over 6 times depth. Well, depth cubed over depth is depth squared. And you still have your divided by 6 here, just like you have it there. So that part right there of the equation is equal to that. But since it's hollow, we subtract the middle part, the B1 times the D1, okay, cubed over 6 times the D all the way from the bottom to the top. And with a circular cross section, the section modulus is, they put P there because they couldn't print out a pi. That is the Greek letter pi, which is 3.141592, etc. Okay, pi times diameter cubed over 32. Okay, well this is a section modulus across the x-axis, but if you had it across the y-axis, you just trade your base and your height around. This wouldn't be the base anymore. This would be the base, and that would be the height. So that's why they have dB squared over 6 instead of BD squared over 6. And same goes for that. Obviously on a circle it doesn't matter whether you're looking at your axis going this way or your axis going this way. A circle is symmetrical, so you're going to have the same section modulus, pi times diameter cubed over 32. Here are some more cross sections. Here's a hollow round pipe, and the section modulus is pi over 32 times big D, the D between the outside diameter, times parentheses outside diameter to the 4th minus inside diameter to the 4th. Okay, here's an I-beam. The section modulus of it is 1 over 6D times base times depth cubed minus that base times that depth cubed. Okay, and across the y-axis it would be, well, these D and B are switched around. Instead of B times D cubed, you have D times, instead of B times D cubed, you have D times B cubed minus D1 times B1 cubed. Okay, and for a triangle, section modulus would be base times the height squared over 24.